Okay, 27. North Carolina State University study in the previous example looked at possible differences in proportion of female and male students who succeeded in the course. They found 23 of 34 women and 60 of 89 men succeeded. Is there evidence of a difference between the proportion of women and men who succeeded? Well, let's look at that. Proportion of women is 23 out of 34. Proportion of men, 60 of 89. So we give out 23 divided by 20, 34, is 67.6%. And 60 divided by 89 is 67.4%. Okay, those are pretty close together. But they're not quite the same, so we don't know, is there a difference? I mean, is this statistically significant, or are they just close enough that it's normal sampling error or sampling difference? Okay, so H0. We're going to assume that the proportion of women is equal to the proportion of men. HA, proportion of women, is there a difference? Not equal to the proportion of men. Okay, conditions that we check, both simple random samples. Now, these really aren't simple random samples, but these are samples from this one particular course, okay, and you could view them as a sample over time because they're all the people in this one course at this one time, but over the time of people taking this course over years, this could be considered a sample, a random sample. 2, the data is independent, no reason not to think so. 3, are these samples large enough? That's going to be the key to looking at. So we're going to assume large enough. And the fourth thing, are the samples independent of each other? And they really, I mean, we can assume they are, but they might not be, because if you have a bunch of men and women taking the courses, if they're somehow related to each other, in any way, study together or not, then they're not really independent of each other. So these are these conditions really don't stand up too well. But we're going to proceed with caution anyway. So let's do this test. If I can get my calculator to turn on. Let's see, it's not wanting to. Okay. Alright, we're going to do it on my calculator on the side, so it's not getting it going. So we're going to do, I'll just talk my way through it because you guys have done this. So it's going to be a 2 proportion z-test. And I'm going to do, the first one is women, so I'll do 23, 34, that's x1 and n1. x2 would be 60, n2 would be 89, and they're not equal to, and calculate, and I get z is equal to 0.024, and my p-value, which is no real surprise, 0.98, which is certainly greater than 5%. Okay, so this is, just happened by chance, right? Got 98% chance of getting these two samples that close together. So since 98 is greater than 5%, I don't have evidence of a difference between the proportion. See, I'm just looking at this up here, right? Proportion of women and men's. Women and men who succeed in this course. Okay, so there we go. We're good on that. Um, and I'm going to let 29, it's in the back. I'm going to leave that alone. If you have questions, you can ask me in class on that one. I'm going to go ahead and go up to 31, and let's take a look at 31 and do 35 and after that. There are emotions influence economic decisions. One way to examine this is to have subjects play the ultimate game against other people and against a computer. Your partner, a person or a computer, gets $10 on the condition that it's shared with you. Your partner makes you an offer. If you refuse, neither of you gets anything. So it's your advantage to accept even the unfair offer of $2 out of 10. Some people get mad and refuse unfair offers. Here are the data on the responses of 76 subjects randomly assigned to receive an offer of $2 from either a person they were introduced or to a computer. So if you get a $10 offer, hey, I'm going to take it because it's good money. $2, no, forget it, I'm not taking it, that's too low. Okay, so what they're saying is if it was offered by a human, it was accepted 20 times and rejected 18 times. If it was offered by a computer, it was accepted 32 times and rejected 6 times. Okay. We suspect that emotion will lead to offers from another person being rejected more often. Okay, rejected more. As I'm thinking, period. More often than offers from an impersonal computer. Do a test to assess the evidence for this conjecture. Okay, so do you understand what's being asked? Let's look at. Okay, so the proportion of if you're rejected by a human is 18 out of 38, and the proportion that were rejected by a computer, if the computer made the offer, was 6 out of 38. So 6 divided by 38 is 15.8, 0.9%. So when a low offer was made by a computer, it was rejected 16% of the time, roughly. When it was made by a human, it was rejected 18 divided by 38, 47.4% of the time. And the idea here is they're saying, hey, if it's by a human, you get emotional and you get upset. What are you doing offering me so low? If it's a computer, it's like, hey, getting mad at it's not going to help me any. Even though I get mad at the automated menu people when I call and want to talk to somebody anyway too. So there you have it. I guess it doesn't work on me. But anyway, another story altogether. So we want to check to see if H0 and HA, we want to check to see is there evidence that you're rejected more often if it's a person. So PH is greater than PC. And we're going to assume that they're equal, because we always assume that they're equal to start with. And then do we have evidence? In other words, is this different, significant, or did this just happen by chance? Okay. So conditions that we need to check for on this are the same as the last one. One, we have to assume that they're random samples or representative samples. We have to assume that the data is independent of each other, okay, that the people are independent in each sample. We have to assume that the sample size is large enough. Okay, and so we're going to make that assumption. And we're going to talk about how, in detail, how do we calculate that in class. And 4, lastly, are the samples independent? Okay. Alrighty. let me go ahead and just address this real quick right here. Sample size large enough. Remember for t-tests, we just said, hey, n has to be bigger than 30 or 40, and we're good by the central limit theorem. Well, here with proportions, we just need to know what makes our sampling distribution normal, and that's when NP is greater than 10 and NQ is greater than 10. So I have to look at my sample size for each sample. 38 times P, in this case it's P hat, 47, 47% and 15%, or 16%, is that greater than 10? Well, 38 times 0.16 is 6. So that's not greater than 10. And so I would check each of these for each sample to see if that's true. And some of them are going to be greater than 10, some not, so I'm going to need to proceed with caution when they're not greater than 10. And we're going to spend some more time talking about this in class on Wednesday, and exactly what's happening with that and why. Alright, so if we proceed, then, and we do this test, it's going to be again, a 2 proportion z-test, and I'm going to do x1 is going to be 18 out of 38, x2 is going to be 6 out of 38, and I want to see if it's greater than. Calculate. And z ends up being 2.96, and the p-value ends up being 0.0015 or 0.15%. Okay, it's pretty small. Not likely to happen by chance. 0.15% is less than 5%. So I have evidence that this guy right here. Let's see, evidence that offers from a person, the offers from a person are being rejected more often than from a computer. Okay, does that make sense? All right, there we go.